Hi everyone. I will start my presentation today. I'm Unju Lee from Department of Electrical and Computer Engineering at the University of Arizona. And today my presentation is about advancing mobility with efficient deep learning. And in my talk today, I prepared a broad and high level overview of this concept and hope that you enjoyed my talk. So today I will talk about Edge AI for mobility and why it matters for mobility application. And also I will talk about efficient architecture for embedded vision and perform a way of conducting performance optimization techniques and also ended up with real world mobility application. So let me start with the artificial perception. And as you may know, these days people are talking about artificial intelligence extensively. And in my lab, I'm working on image analysis, computer vision, and medical image analysis as well. And artificial perception is basically you try to use a sensor to understand the world. And example in computer vision domain, basically you can use object detection or tracking or classification as well to understand the world around you. And in mobility application, you can use different type of input, such as images, or it could be audio and other type of image modalities, such as infrared and so on. And also artificial intelligence, as you may already know, their performance has been proven outstanding so far. And goal of AI is to mimic core cognitive activities of human thinking. And this due to extensive training data set and also computing resources, foundation model has achieved outstanding performance. And foundation models trained on large amount of data applied in multitask show possibility in different domains. Not only mobility application, but also in medical imaging application, you have seen lots of use cases as well. And vision language model, which called as a VLM, you can use different type of modality that gives different applications as well. So tasks in computer vision models, these are some of use cases, including classification and object detection and segmentation. So for those who doesn't have understanding of these vision tasks, classification is to classify what you observe in images, and also object detection is basically you are getting for different corners, which is bounding boxes, and you also are getting a classification of certain object in the images. And also segmentation, you try to get a pixel level classification. So if you have images and also object, if you are interested in getting the contours of objects, so basically segmentation is the task you are interested in. And also other computer vision tasks, such as image registration and localization and mapping, those are pretty well-defined problems and also can be applied in different mobility application. And as I mentioned before, vision language model has achieved outstanding performance, and also this is end-to-end AI. So basically, you are trying to get some output using images and also text as well. So when you are deploying those computer vision algorithm in mobility application, I have prepared some of the use cases. So definitely autonomous vehicle systems and also robotic and also some agricultural application. And if you are interested in surveillance video application, definitely Edge AI and also computer vision techniques should be investigated. So these are some of the examples in mobility application. So in the left figure, this is one of the projects that I'm working extensively in my lab. So we are trying to collect electric vehicle data set so that we can identify specific electric vehicle within images. And also by using AI and also computer vision techniques, you can get the bounding boxes of certain classes, such as vehicles or pedestrian or bus and other classes as well from UAV drone imaging systems. So the key thing is, in this research topic,
we are interested in getting robust detection output as well as lower latency so that you can get almost like real-time processing capability. So common AI challenges, as you may already know, so you have to solve adaptive scaling, meaning the system must adjust to hardware limitation, because if you are using different type of devices, they should have a different resource constraints. So you have to think about how to carefully take care of this adaptive scaling. And also, often you have to take care of this real-time processing capability so that you can deploy your algorithm in certain devices. For example, if you're using NVIDIA Jetson or different type of devices, you should take care of this resource constraint system and then try to achieve real-time processing. And also, you must detect delays and catch up without data loss. For example, if you are using image sequences, basically if you are using video data set for vision application, this is also, data loss is something you have to take care of as well. So why edge processing is required for mobility? So as you can see in the top right figure, so if you are working on autonomous vehicle application or UAV drone imaging system, you have to take care of real-time processing and then how to deploy those algorithms in device, and also how to minimize the latency as well. So performing AI inferences directly on device or very close to them, which is edge AI, is essential for various mobility applications, including autonomous vehicle system or other mobility application. And also you might be interested in reducing communication latency and bandwidth load, and also real-time decision in safety critical application is also important in mobility application. And also you should, or you might be interested in privacy issues as well when you are using a data set or data streams. So if you are working on edge AI with computer vision tasks, this would be some requirements. So to ensure reliable real-time decision making, mobility system require a careful balance of speed. It would be, it could be FPS or it could be latency, and also accuracy. You might be interested in getting robust detection or tracking, or it could be segmentation as well. And also efficiency is pretty important. So achieving this often depends on maintaining low computational cost, especially on resource-constrained edge devices. So that's why I try to talk about efficient deep learning architecture today. So hope that you can understand some core concept, although I would not go in depth, but hope that you can understand the high level of understanding of each concept. So I will start with the evolution of neural networks and efficient models. So you may have some understanding of convolution neural networks. So I will start with the pre-deep learning approaches before 2015. Because in our lab, we are working on computer vision. And before deep learning architecture, people were interested in developing handcrafted features, such as histogram of oriented gradients or surf or shift. That type of algorithm is to extract some of the feature within the images. And if it is image sequences, you are interested in getting some motion or trajectory of certain objects. So to achieve or address those problems, you can use HOF or HOF3D. And if you are interested in getting some pose estimation, there are some algorithms you can use. And if you are try to get some trajectory, improved dense trajectory method is pretty well-defined technique you can utilize. And IDT removes the influence of camera motion so that you can find some meaningful feature in image sequences. So when you have those features extracted using different type of algorithm, there are a different type of inference mechanism you can utilize, such as bag of features and feature vector, and also SVM or HNM or CRFs. Those are some of representative method you can utilize. But limitation is that a small data set with simple activities were available at the time, and also limited ability to model group dynamics and complex interactions. So before 2015, those are some of the representative methods you can utilize in terms of feature extraction and also inference mechanism. So let's talk about deep learning, including convolution neural network and some other spatial temporal modeling. So early CNN-based approaches from 2014. So basically 2D CNN is a very powerful architecture you can utilize. So if you have image sequences, you can just apply those 2D CNN on individual frames and you can extract the features and get some output you are interested in. So, and if you are interested in video processing, what you can do, you can use those video as a first path. And also you can use this optical flow that shows the motion in the image sequences in a separate path. And then you can just pass through a different stream and then combine it all together to get the output or prediction you are interested in. And another advancement in spatial temporal modeling from 2016 to 2021, there were different type of architecture provided, such as TSN and I3D and also CSN, as you can see here. So basically you are inputting video clips and you are using 3D CNN so that you can handle spatial information as well as temporal information at the same time to get prediction accordingly. And let's talk about 3D CNN further. So basically 3D CNN model works fine with the video input, but they can just take care of short temporal attention span up to a few seconds. So when you are using videos, the duration should not be just a few seconds, but when you are using 3D CNN, there is a limitation of using it. But in the end, you might be interested in longer video understanding. So anyways, 3D CNN works fine, but you may need like a powerful architecture to obtain robust output. And so, and there was a limitation of using 3D CNN. And later on, now Transformer released, and these days people are extensively using vision transformer just because their performance has proven outstanding. And especially vision transformer that utilize self-attention for spatial feature learning, they have shown very excellent performance in different vision tasks. So this vision transformer has been used in different type of video application and also other architecture, including Timesformer, Video MAE, and version 2 as well. And VIVIT has been released and their performance has been proven very excellent. But although their accuracy was powerful, still the limitation is that they require high computational cost, and also there is data efficiency issues. And these are some transformer characteristics, and this architecture is able to naturally handle any input which can get tokenized. Here, tokenized, if you are using images, you can make a patches and each patches can be tokenized. But if you are using videos, each image can be considered as token as well. So how do you define token in your application? You can use different approaches to solve problem. And also, this architecture can handle long-range dependency and better scene understanding. So that's why when you're using 3D CNN, you can just take care of a few seconds, but this transformer works pretty powerful when you are approach this problem in a holistic way and also try to have a global understanding as well. And then later on, Foundation Vision Language Model has been released. So this Foundation Vision Language Model is powerful when you are dealing with multiple modality. For example, if you are using images or videos or audio, which is different, or different type of input data source. And what if you are interested in using language data set, you can use a separate encoder for different type of input source, and then you can use transformer to combine all together. And cross attention basically works for this capability. And also the output would be the prediction you are interested in. So the key thing is you are using different type of encoder to extract the features and get the embedding, and then try to use a transformer to combine all together and then get the prediction, which would be your final output interested in. So when you are using multiple input sources from different modality, you can use input tokenization in transformer approaches. So video, you can use pre-trained visual encoder such as Timesformer, VI-VIT, and Video MAE and version 2. And they have their own approaches to extract the features. And audio is, you can use some approaches such as WAV to VC version 2, and also Open Smile or Whisper from OpenAI is something you can use to extract feature when using audio data set. And text, definitely people are working in this domain extensively, and Llama or T5, also GPT model is working very well with text encoder. So transformer-based processing, you can use cross-modal fusion through shared attention layers, and some common architecture is Video Llama and also OmniVL. So as I said, in mobility application, you may use images or sometimes you are using video. So this foundation vision language model could be versatile and you can use extensively with other application. It could be used for video understanding or activity understanding as well. But still, there is a limitation of VLMs for activity understanding with the video data set. And the limitation is that most reasoning and understanding in VLMs for action detection is handled by large-scale language models. And while visual encoding has seen limited improvement. So when you are using this VLM, visual encoding has a limited improvement. So challenges in visual encoding when you are using this visual language model, compression on motion information and losing some temporal granularity would be the issue, and frame sampling and keyframe-based processing resulting motion discontinuity would be some challenging factor when you are using this VLM for activity understanding. So starting from with CNN and also 3D CNN, also transformer, you can use this type of deep learning models to solve different type of vision application, and the strength are precise spatial and temporal localization when trained on well annotated data sets. So here you may need high quality of annotation. So when you are using object detection, the bounding box annotation should be well collected so that you can get robust output. And also fine-grained motion encoding and modeling short to medium range context are the strength. And also highly tunable for domain-specific tasks. So when you have small sets of data set, you can use fine-tuning and try to have the model tailored to your specific application or problem. But still, limitations are as follows. You may require large label data set to generalize well, because especially when you're using large-scale model, you may need a large label data set as well. And also, the limitation is that lack of semantic reasoning would be an issue when you're using this type of approaches. So these are some basic of CNN, also 3D CNN, as well as transformer for some image application and video processing application as well. But for efficiency, there were several architecture released. MobileNet are one of representative one, as you may know. So this one is a pretty old one because it was released in 2017, and this is faster than smaller and fast smaller than VGG16, which is one of representative CNN model. Basically, they are using depth-wise separable convolution for efficient computing on mobile devices. So as you can see in the right figure, so they are not using convolution, or they are not using kernel in all whole channels, but they try to use a channel separately and also use a kernel in different channel, and then they are using point-wise convolution. So basically, they are using one-by-one convolution and then combine them all together. So by using these two stages, including depth-wise convolution and point-wise convolution, they have achieved a faster and smaller architecture when compared with the existing convolution neural network. And next year, MobileNet version 2 has been released, and their performance is better than previous version, definitely. So their performance is 0.3 times faster and smaller. And basically, they are using linear bottleneck instead of nonlinear bottleneck. So typically, you are using some activation function so that you can achieve non-linearity, such as ReLU or other type of activation function. But in these approaches, they are using linear bottleneck, and also they have this residual connection, and also some projection convolution in the last stages. So by combining all these modules, they have achieved a faster performance. Another representative one that people are using for efficiency is EfficientNet. So this one is using a compound scaling method so that you uniformly adjust network depth, width, and also image resolution as well. So by using this compound scaling method, they have achieved outstanding performance in terms of efficiency. And this balanced scaling strategy allows high accuracy and also fewer parameters. So personally, I have used this EfficientNet with different type of application, including medical domain, medical imaging application, and also some basic object detection, just because they have a different complexity starting from B0, and also they have a B7. So you can flex it, you can use this model with better flexibility. So if you are using different type of resource constraint system, you can just select the one that is suitable for your application. So those are some of representative architecture. And these days, people are interested in neuromorphic computing. So that's why I included one example for spike YOLO. So many of you might know YOLO algorithm for object detection. But this is a paper published in 2024 in CCS. So they are containing backbone and also unit type of encoder decoder. And if you see this macro design, they have a backbone and also a neck and also head for getting the bounding box output. But if you see the micro design, they are combining the modules so that you can achieve efficiency, including depth-wise convolution and also channel-wise convolution as well. So those are some architecture that you can achieve end-to-end AI. And also, I have prepared some examples that you can achieve efficiency when you are using AI for your application. So, for example, if you are trying to solve some computer vision tasks, typically there are many ways to solve the problems. And one simple way to think of solving the problem is multi-stages. For example, if you are trying to solve tracking problem, a simple thing you can do is getting detection in individual image frames and connect them to get the trajectory so that you can achieve tracking output. But if you are using these data-driven approaches, basically AI, you can have end-to-end solution. So you don't have to tackle this problem by approaching most stages, but you can have like one stage algorithm so that you can have this output that you are interested in. So if you are working on hand gesture, For example, as I prepared in this slide, you don't have to have some hand detection and skeleton gesture classification. You can have just one stage so that you can have an efficient output as a one stage model. And also data-driven approaches are valuable because you can also input multiple data sources as a one input. So for example, if you are working on object detection in different multi-view or road scene images, so you can also use those multi-view images as a one input, and then you can use transformer or other type of architecture to have a better or robust detection output. So BEE former is a one popular architecture you can use to solve this problem. So what if you have a multi-view images, and what if you are interested in object detection? BEE former is working pretty well in terms of this problem. But as I mentioned earlier, when you are using transformer, there are some limitations because they have a higher computational complexity. So typically they have a big O n to the 2, and which is very poor. So people try to resolve this issue by proposing other architecture. So state space models, they try to resolve the issue of high computational complexity. So rather than big O of n to the 2, so basically they have this linear big O annotation, and they are using hidden state acts as a lossy bottleneck, and this gives a much faster inference time. And Mamba-like linear attention is also a way to resolve the issue of high computational complexity. So rather than big O n to the 2, so they try to reduce the complexity by having linear attention. And another approach is to achieve efficiency. You can use embedding models. So embedded vision project, when with a dynamic and evolving object sets, embedding models enable the addition of new classes with retraining. So they support fine-grained search and recognition of previously unseen categories. So how you can do is basically you can use multiple images as an input, and you can have embedding model so that you can map those embedding in higher dimension spaces. And basically, if you have a similar object, you try to make a closer. But if you have a dissimilar object, you try to make them far apart. And to achieve this embedding or better representation, you can use different type of loss. So contrastive loss is one of the representative one, and also triple loss or other margin loss could be considered as well. So including different type of architecture, you can use some method for embedding models, but also you can use input compression, which I will describe in this slide. So this is one of my earlier work. So you can also work on model compression in your architecture, but you can also compress information in your input. So in my earlier work, I try to compress input data set by using frequency domain analysis. So when you have this 3D cube and try to use 3D CNN, their computational burden is pretty high. So to reduce the computational burden, what I did is try to use DCT, so basically discrete cosine transform, so that you can extract some critical information and then use them to get final classification. So if you are using this frequency domain analysis, you don't have to use all the information, but you extract some of meaningful features and then feed them in CNN so that you can achieve good accuracy. So in my earlier work, I worked on image compression and also feed them in 3D CNN and 2D CNN. and then try to get some trade-off curve between accuracy versus inference and also PS and other power consumption as well. You can work on image compression, but in the meantime, people are working on transformer actively, but you can also try to reduce the complexity in transformer itself as well, because they have a self-rotation, cross-rotation that requires a large computational burden, but somehow you can work on tokenization or adaptive layer so that you can minimize the computational burden within a transformer. So this is also one of my work that is under preparation right now. So by using some adaptive layer and also tokenization, I have prepared some of the representative method, and then our method has been superior to other existing method. So typically when you are using efficient architecture, you have to take care of accuracy, speed, and also power consumption and memory usages as well, so that you can prove your algorithm is superior to other existing method. So those are some of the methods you can use for efficient architecture for embedded vision. So next, I will talk about performance optimization techniques. And knowledge distillation is one of popular method you can use for model compression. So this is my earlier work regarding knowledge distillation-based segmentation. So when you are using mobility, when you are working on mobility application, you may use large data set or extensive input data set because they have higher image resolution, and also typically it will be image sequences with a large scale data set. Similarly, in medical domain, typically their input resolution is pretty high, and also sometimes you are working on 3D voxel, which requires large computation. So that's why I try to use knowledge distillation to achieve efficiency. So I try to use knowledge distillation for image segmentation, and existing transformer, as I mentioned, their performance is pretty good. When you're using trans-unit, basically architecture combining transformer model and unit type of architecture, which is widely used in medical domain. Their performance is pretty good, but still limitation is that they may require extensive computational burden, which hinder real-time processing capability. And also in trans-unit, they have multi-head self-attention, which is core component in transformer model, but that gives a quadratic complexity. So that's why you may need a large computational burden when you are getting pixel-wise classification. So because of this limitation, real-time processing cannot be achieved. And typically in mobility application and medical imaging application, real-time processing capability is valuable because clinicians would like to get the image analysis in real time, and also mobility application, you may want to solve the problem that can give a near-time prediction output. So in conventional trans-unit architecture, you may have this multi-head self-attention. So basically they have a CNN backbone as well as transformer layers and also decoder part, which gives you final segmentation output. In one of our work, we try to use just self-attention instead of multi-head self-attention, so that you can minimize the computational burden, and also you are using some of the feature in an identical way and try to have some portion of parameter that can be learnable. So by doing these approaches, I can achieve better or efficient approaches to get final segmentation output. And also knowledge distillation is a popular way of solving efficient problems. So this method transfers knowledge from a larger teacher model to a smaller student network. And there are many ways of solving this problem. When you are using knowledge distillation, you can approach this problem using response level KD. So this one actually try to use last stages of large, so that you can achieve knowledge distillation, but also you can approach this problem using intermediate level. So basically you are using feature extracted in the intermediate level from teacher and student network, and then you use different type of loss so that you can achieve knowledge distillation. So in our work, we try to use a single head attention as well as multi knowledge distillation approaches. So basically we have used response KD and also intermediate KD. So we are using feature level matching and also last stage matching stages as well. So in our lab, we are working on medical domain, but I believe a similar technique can be adopted with mobility applications as well. So in our studies, we have used this BTCV dataset, which is one of the popular one in medical domain. And this is a CT scans, and approximately they have 80 axial slices per scan, and image resolution is 500 by 500 with the different classes. And also we have used a catalog, which is an eye image data set, and the target problem here is a segmentation. So by using our approaches when comparing with the vanilla transit unit, our approach is using a single head self-attention and also knowledge distillation have achieved better latency, which is a lower latency, and also compatible segmentation output as well. So in our study, we have compared our method with other existing method and also some ablation studies, and we have shown that our approach is very efficient when using high image resolution. So key message here is that when you try to achieve efficiency, especially using AI, many people are using knowledge distillation, but you can work on multi-scale knowledge distillation, not only response level, but also feature level matching would be alternative approaches. So when I have a discussion with the NVIDIA engineering team, they were interested in using knowledge distillation for object detection. And object detection is much challenging compared to segmentation, because anyway, you have to take care of coordinates, and also somehow there are more issues when solving object detection. But some industrial companies are very interested in using knowledge distillation to achieve efficiency when solving different type of computer vision tasks. And then I will talk about another approach, which is parameter efficient fine-tuning. So when you have large pre-trained weight, you can work on fine-tuning so that you can approach your problem that would be domain-specific tasks. So LoRa, which is low-rank adaptation, is one way to approach this problem. So when you fine-tune the model, you may require to retrain the architecture, and you have to somehow require some additional burden. But LoRa, which is low-rank adaptation, or QLoRa, which is quantized LoRa, this is a smart way of solving this problem. So basically LoRa, which is low-rank adaptation, you freeze original model weight and try to add small trainable adapter. So by using low-rank approximation, you can have this small trainable adapter so that you can minimize the number of parameters you have to learn. And this approach requires lower memory and also training costs, and also it maintains model performance with minimal overhead. QLoRa is just extension version by using quantized quantization method, and often the only feasible option under tight memory constraints. So both of them are pretty clever way of achieve efficient AI systems. And then another key concept that might be valuable would be post-training optimization and quantization-aware training. So post-training quantization is a method used to reduce computational resources for inference, and it maps the data from a high precision floating point to a lower precision. So if you have a floating point, a parameter, so basically you try to map it in an integer value. And this process is done after training the model and before inference. So as you can see in this figure, so what if you have this pre-trained model, and you can use some small sets, which we refer to calibration data, and you will go over a calibration step, which is for generating quantization parameter based on collected statistics. So in this way, this is a very simple way of approaching problem, because you are using original pre-trained model and you are using small sets of calibration data so that you can generating quantization parameter. So this is pretty simple yet effective. And calibration data set, as I mentioned, this helps determine the dynamic range of activation in each layer of neural network. So you are using some small portion of data set, typically 1 to 5% of the data, and this value may vary depending on the complexity of the model or the post-training quantization technique used. So this is a simple way of achieving quantization without training the neural network. And advantage, again, this is very easy to implement, and this reduced memory footprint, especially relevant to edge devices, and faster inference would be advantage in this method. But disadvantage, you will have accuracy loss, because anyway, you are not retrain the model, but somehow you are using small portion of the data set to obtain some parameter quantization configuration. And this is sensitive to data distribution and less effective on complex models. And they have a couple of limitations, and this method is not, this cannot fine-tune weight post-quantization, and they cannot handle outliers adaptively without specific techniques. And this is another technique would be that is more complex. Quantization-aware training would be alternative solution to somehow maximize your performance. And this is a more complex method than post-training quantization, but often better for model accuracy. And this one involves retraining the model based on the same training data set. So as you can see in the right figure, their approach is a little different. So once you have pre-trained model, you would go through quantization, and you are using same training data set, and you would have a training fine-tuning, which defines quantization configuration. And the advantage of this quantization-aware training is higher accuracy after quantization, but disadvantage anyway, you have to retrain this, so time consumption process, and also somehow you need access to labeled data set. And the limitation, as you can see, more complex to implement than post-training quantization, and the feature of this technique may vary depending on the framework used. And the other way of achieving optimization is software and hardware co-design. And Meta is actively working on these approaches because they are interested in AR/VR application, especially this Meta Quest version 2 and version 3. They also need some real-time processing and low latency as well to achieve some application. And performance profiling often shows that camera software is limited by memory. So somehow they need a very well-designed optimization. And Meta's own memory optimization approach, custom containers, as well as pre-allocated memory at startup, they have achieved CPU reduction and also fewer memory allocation for VR cameras. So if you are working on some hardware application, co-design with software and hardware would be very valuable in practical application. So in real-world mobility application, the method that I introduced today would be very valuable. So for example, if you are working on autonomous SLAM or navigation, so somehow you are using multiple input data, which could be RGB or DepthMed or other some semantic labels as well. And if you are working on SLAM, and also if you try to achieve real-time processing, those efficiency would be very valuable. And also 3D reconstruction, definitely, if you are working on point cloud model or some 3D reconstruction problem, this efficiency would be valuable. And also self-driving cars, not only semantic segmentation, but also tracking system or pedestrian trajectory estimation, you may need some real-time processing capability. And also, these days, people are interested in robotic system. They may need visual intelligence, and also they have many applications, such as real-time fault detection and also pick and place operation in factory scenario. So those efficiency in AI system would be really valuable. And again, some of the challenges would be computational and hardware constraints, because you may need different type of requirement. So some people would are using NVIDIA Jetson, or some people are using some Qualcomm device, for example, and they may have a different configuration. So that's why you need to take care of those requirements, and also have to work on data like efficiency. And also model management at scale would be very important also. When you're using AI, definitely safety and also trust would be very much important. And yes, and our lab is working on embedded computer vision, try to develop efficient AI systems. And this is pretty much I prepared regarding efficiency AI. And if you have any questions about the topic that I covered, I'll be happy to answer your questions. Thank you.